Section 2.5. Continuity. The outline of this video is as follows. We will discuss the concept of continuity, starting with the intuitive idea of what it means for a function's graph to be unbroken. We will then formalize this idea with a precise, three-part test that a function must pass to be considered continuous at a specific point. Next, we will explore what happens when a function fails this test by examining the different types of discontinuities, such as jumps or holes in a graph. From there, we will cover some important properties of continuous functions, like how they behave when you add or multiply them. We will also introduce a powerful result called the intermediate value theorem, which guarantees that a continuous function takes on every value between any two of its points. Finally, we will look at a technique called continuous extension, which is a method for fixing certain types of discontinuities in a function. Let us begin with the intuitive idea of a continuous function, which is a concept we rely on to model processes that change smoothly. A function is considered continuous if you can sketch its entire graph over its domain in one single, unbroken motion, without ever lifting your pen from the paper. This means that as the input to the function changes, the output varies consistently and predictably, without any abrupt jumps or gaps. For example, when we plot data points from an experiment, like the distance an object has fallen at several points in time, we often connect them with a smooth curve. In doing so, we are assuming the underlying physical process is continuous between our measurements. So the essential thing to remember is that a continuous function is one whose graph has no breaks, holes, or sudden jumps. To build our intuition for what makes a function continuous, let us look at a graph with several breaks. At the point x equals 1, the function is not continuous because it jumps. The limits from the left and right are different, so an overall limit does not exist. The function is also not continuous at x equals 2, but for a different reason. The limit as x approaches 2 does exist and equals 1, but this value does not match the actual function value, which is f of 2 equals 2. We see a similar issue at the endpoint x equals 4. In contrast, at x equals 3, the graph is unbroken because the limit as x approaches 3 is 2, and the function's value, f of 3, is also 2. For a function to be continuous at a point, its limit must exist, and that limit must equal the function's actual value right at that point. Let us formalize our idea of an unbroken graph with three precise definitions of continuity at a point. First, for a function f to be continuous at a point c, its two-sided limit as x approaches c must exist and be exactly equal to the function's actual value at c. This ensures the point is right where the surrounding graph predicts it should be. We can also look at this from one side at a time. A function is right continuous if its limit approaching c from the right, meaning from larger values, equals the function's value. Likewise, it is left continuous if the limit from the left, or smaller values, matches the function's value. For example, at the left endpoint of a closed interval, we only need right continuity for the graph to feel connected. The key takeaway is that for a function to be fully continuous at any interior point, it must be both right continuous and left continuous there. To move beyond just looking at a graph, we can use a formal three-part checklist called the continuity test to determine if a function is continuous at a specific point. First, the function must be defined at the point we are testing, which we can call c. This simply means that f of c must exist, so if there is a hole or an asymptote at that point, the function fails this first step. Second, the limit of the function as x approaches c must exist, which ensures the function is heading toward a single, finite value from both the left and the right side. Finally, and most importantly, the limit from the second step must be exactly equal to the function's actual value from the first step. For a simple parabola at x equals 2, its value is 4, and the limit it approaches is also 4, so it passes. If a function satisfies all three of these conditions, it is continuous at that point. To make the idea of one-sided continuity concrete, I will walk through a few important examples. A simple case is the function f of x equals the square root of the quantity 4 minus x squared, which is continuous across its entire domain. Things get more interesting with the unit step function, which jumps from 0 to 1 at x equals 0. Because the limit from the right matches the function's value, it is right continuous. But since the limit from the left does not match, it fails to be fully continuous. The greatest integer function, which rounds numbers down, provides another great illustration. For any integer n, the limit as x approaches from the left is n minus 1, while the limit from the right is n. Since the function's value at n is also n, it is right continuous at every integer, but not left continuous. This shows that being continuous from one side does not guarantee overall continuity. Now that we know the test for continuity, let us explore the common ways a function can fail that test, which we call discontinuities. The simplest case is a removable discontinuity, where a function's limit exists at a point, but the actual value there is either missing or different from the limit. This is like a single hole in an otherwise smooth line that we could easily patch. Next is a jump discontinuity, which happens when the function approaches one value from the left and a completely different value from the right, causing the graph to leap from one level to another. A more dramatic failure is an infinite discontinuity, where the function shoots up toward infinity, like f of x equals 1 over x squared at x equals 0. Lastly, an oscillating discontinuity occurs when a function fluctuates so wildly, like sine of 1 over x near 0, that it never settles on a single limit. Understanding these types helps us classify exactly how and why a function is not continuous. Now that we have a formal definition for continuity, I want to show you a visual catalog of the different ways a function can fail to be continuous. Graph A shows a perfectly continuous function for comparison with no breaks at all. The other graphs illustrate various types of discontinuities. In graphs B and C, we see a removable discontinuity, which is essentially a single hole in the graph that we could easily patch by defining just one point. A more significant break is the jump discontinuity in graph D, where the function abruptly leaps from one value to another. Finally, we have more complex cases, such as the infinite discontinuity in E, where the function value heads toward infinity, and the oscillating discontinuity in F, where the function varies so erratically that it never settles on a limit. The main thing to remember is that we can classify the specific way a function's graph is broken. Now that we can identify a few basic continuous functions, we can use them as building blocks to construct more complex ones. This is possible because continuity is preserved under standard arithmetic operations. If you have two functions that are both continuous at a point C, then their sum, difference, product, and any constant multiple will also be continuous at that same point. The same holds for powers and roots, as long as they are well defined. The only major exception to watch for is division. The quotient f over g is continuous only if the denominator function g is not 0 at the point C. A great example of this principle is that all polynomial functions are continuous everywhere, and all rational functions, which are just ratios of polynomials, are continuous everywhere except at the points where their denominator equals 0. The key takeaway is that you can combine continuous functions arithmetically, and the result will remain continuous. I will now explain a powerful rule that shows how continuity is preserved when we combine functions. This rule, known as the continuity of composite functions, states that if you compose two continuous functions, the resulting function is also continuous. A composite function, written as g composed with f, is what you get when you apply one function, f, and then apply a second function, g, to that result. The logic is that if the input x is close to a point C, the output f of x will be close to f of c because f is continuous. Then, Since g is also continuous, g of f of x will be close to g of f of c. For example, the function y equals the square root of the quantity x squared minus 2, x minus 5, is a composite of a continuous polynomial and the continuous square root function. The main takeaway is that you can build complex, continuous functions from simpler ones. I will now explain a powerful theorem for finding the limit of a composite function, where one function is inside another. A theorem states that if an outer function g is continuous at a point b, and the limit of an inner function f of x as x approaches c is that same point b, then we can essentially pass the limit operation through the outer function. This means the limit of g of f of x is simply g applied to the limit of f of x, which equals g of b. Let us use the example to make this concrete. We want the limit as x approaches pi over 2 of cosine of the quantity 2x plus sine of the quantity 3 pi over 2 plus x. Since the outer cosine function is continuous, we can move the limit inside. This gives us cosine of the limit of the inner expression. That inner limit evaluates to pi plus sine of 2 pi, which is just pi plus 0. Our final result is cosine of pi, which is -1. In short, continuity allows you to evaluate the function at the limit of its input. I am going to introduce a powerful property of continuous functions called the intermediate value theorem, which essentially guarantees that these functions do not skip over any values. The theorem states that for any function that is continuous on a closed interval from a to b, it must take on every single value between its starting height, f of a, and its ending height, f of b. This means, if we choose any target value, let us call it y0, between those two heights, the theorem promises there is at least one input, c, within our interval that produces that exact output. Geometrically, this is very intuitive. If you draw a continuous curve from one point to another without lifting your pencil, any horizontal line you draw between the start and end heights must cross your curve at least once. The key takeaway is that continuity on an interval ensures the function's graph is a single, unbroken curve. One of the most practical applications of the intermediate value theorem is for locating the roots of an equation. A root is simply a value of x that makes a function f of x equal to 0, which is where the graph crosses the x-axis. The theorem tells us that if a function is continuous on a closed interval and its values at the endpoints have opposite signs, it must cross the axis somewhere in between. For example, let us show that the equation x cubed minus x minus 1 equals 0 has a root between 1 and 2. Our function is a polynomial, so we know it is continuous everywhere. Atx equals 1, the function's value is -1, and at x equals 2, its value is +5. Since the function is continuous, and its sign changes from negative to positive, the theorem guarantees at least one root exists between 1 and 2. So a sign change for a continuous function is all we need to prove that a solution exists. We can often repair a function that has a single point missing by creating what we call a continuous extension. This situation arises when a function, f of x, is undefined at a point, let us say x equals c, but the limit as x approaches c does exist and equals a finite number L. To create the continuous extension, we define a new function, f of x. This new function is identical to our original function, f of x everywhere, except at the point c. Atx equals c, we explicitly define the value of f of c to be equal to the limit, L. You can picture this as simply filling a single hole in the graph of the function to make the curve complete. This technique works only for these removable discontinuities, not for jumps or vertical asymptotes. The key idea is that we create a new continuous function by defining its value at a point to be its limit there. Let us see how we can fix a function with a hole in its graph by creating what is called a continuous extension. Consider the function f of x, which is the fraction with x squared plus x minus 6 in the numerator and x squared minus 4 in the denominator. This function is not defined at x equals 2 because that input makes the denominator 0. To find the location of the hole, we can simplify the function by factoring. The numerator becomes the quantity x minus 2 times the quantity x plus 3, while the denominator becomes the quantity x minus 2 times the quantity x plus 2. For any x not equal to 2, the common factor of x minus 2 cancels out. This reveals that the function behaves just like x plus 3 over x plus 2. By taking the limit as x approaches 2, we find the value that plugs the hole is 5 over 4. The continuous extension is the new function f of x equals x plus 3 over x plus 2, which fills the gap and makes the function continuous at x equals 2. Let us recap the essential ideas about continuity, which is a foundational concept in calculus. We started with the core definition. A function is continuous at a point c if its limit as x approaches c is exactly equal to its value at c, ensuring the graph has no breaks. We then explored the different ways a function can fail this test, such as having removable holes, jumps, or infinite discontinuities. Importantly, we saw that combinations of continuous functions, like sums, products, or compositions, are also continuous, which makes them very predictable. This predictability leads to the powerful intermediate value theorem, which guarantees a continuous function on a closed interval hits every value between its endpoints. This theorem is incredibly useful for proving that equations have solutions, for example, by showing a function must cross the x-axis. The main thing to remember is that continuity smoothly connects the limiting behavior of a function to its actual value at a point. Let us apply the continuity test to find a value for the parameter a that makes this piecewise function continuous at x equals 2. For continuity, 3 conditions must be met. First, the function must be defined at the point, and the definition tells us that f of 2 equals 5. Second, the limit as x approaches 2 must exist, which means the left-hand limit must equal the right-hand limit. To find the left-hand limit, we use the expression for x less than 2, which gives us a times 2 squared minus 1, or 4a minus 1. The right-hand limit uses the expression for x greater than 2, which is 2 plus a. Setting these equal, we get 4a minus 1 equals 2 plus a, which solves to a equals 1. The final condition is that this limit must equal the function's value. With a equal to 1, the limit is 3, but the function's value is 5. Because 3 does not equal 5, no value of a can satisfy all 3 conditions, so the function cannot be made continuous at x equals 2.